our great pleasure to have Dr. Philipp Walk and Dr. Peter Jung to join us today for this nice presentation on the new waveform called MOCZ. And I'm going to share a little bit of background of our OTFS SIG. And this is basically a platform for OTFS, but now we actually broaden our horizon by introducing more waveforms. Therefore, why MOCZ is actually one of our first guests here to share with us there are new developments and advancements. So if you are interested in this special interest group, you can join us anytime by this mailing list. And I'm going to introduce today's topic. It will be a new physical waveform for palette-free integrated communication and sensing. And this topic is called MOCZ, this waveform. And I'm going to give a quick introduction of the speakers. We have a first speaker, Dr. Philipp Walk, who received a master's degree in mathematics physics from the Technical University of Berlin in 2006, and a PhD degree from the Electronic Engineering Department, TU Munich, in 2014, under the supervision of Holger Burke, where he continued as a postdoc until 2015. In September 2015, he received the DFG postdoctoral fellowship and joined the group of Babak Hasbi in Caltech, USA, and where this new modulation and the multiplexing scheme called MOCZ was invented. And from February 2016 and May 2016, he was a fellow at the Hausdorff Trinster program, Mathematics of Signal Processing in Bonn, Germany. And from March 2018 to March 2019, he was a postdoc researcher in the group of Hamdi Jafani at the University of California, USA. From 2019 to 2021, he was working as the researcher in the various research and standard department at Future V. And from 2021 to 2022, he was working in a project with the South Africa at the chair of Professor Joseph Carey at TU Berlin. And in 2022, he started this BMWK-funded Exist research transfer project on MOCZ, where he founded his team and the MOCZ GmbH in March 2023. Since January 2024, the team is working full-time on a prototype for MOCZ as a new solution for integrated communication and sensing, supported by the BMBF project on MOCZ, this project. Okay, we have our second speaker, Dr. Peter Jung, who received the Diploma of Physics in High Energy Physics in 2000 from Humboldt University, Berlin, Germany, in cooperation with DESY Hamburg. He since 2001, he has been with the Department of Broadband Mobile Communication Networks from Fraunhofer Institute for Telecommunications, HHI, and since 2004 with Fraunhofer German Signal Lab for mobile communications. He received a PhD degree in 2007 under the supervision of Holger Burke and at the TU Berlin, Germany. Peter Jung is working at TU Berlin in the field of signal processing, sensing, information and communication theory and machine learning. In 2021, he was a visiting professor at TU Munich and associated with the Munich AI Future Lab, working in the field of uncertainty quantification. And since 2023, he is with the Germany Ultra Space Center, leading the group of computational sensing and AI. His current research interests are in the area of compressed sensing, machine learning, time frequency analysis, dimension reduction, and quantum computing. He is giving lectures in compressed sensing, estimation theory, and the inverse problems. Dr. Jung is also a member of VDE-ITG and the co-inventor and co-founder of the MOCZ. Okay, I'm going to stop sharing. And without further ado, please join me to welcome our speakers, Dr. Philipp and Dr. Peter, please.
Thank you very much, Jung, for this nice introduction and moreover for this organizing of this wonderful workshop. I think it's a
Thank you.
great idea to have such a platform and to basically discuss also alternatives to our existing wireless technologies we have in the standards right now. And I think this is, yeah, this is great to have this discussion. Let me share my screen now. And so, all right. I think everybody can see now, hopefully. Is it all right? Yes.
Yes.
Okay. So MOCZ is, as you mentioned already, it's a new waveform, which was invented by me, Peter Jung, and my host professor, Babakar Sivi at Caltech in 2017. So it dates already a while back, now 7 years basically. And this invention is old. And by that time, I didn't was planning to start a company, which we did now. And but I saw the potential right away, so that's why we also patented. MOCZ is, on the nutshell, a completely new physical waveform, which uses a different, let's say, domain, right? Like OTFS is accessing the delay Doppler domain. We basically using a zero domain, which I explain later. And the advantage of that waveform is it is completely pilot-free. There is no need to insert pilots to do reliable communication and sensing at any receiver. That is basically the big potential of that. So it really is a truly waveform which can integrate communication sensing in one shot, in one transmission. The basically the invention and the main work was done. There was a postdoc at Caltech. So Caltech is basically one of our partner, and TU Berlin was also where Peter was working for. It's also our partner, and together with them we filed the technology as patented. So the patent, we have already 20 worldwide patents out, and also have now filed as a company an own patent. So we are also okay to talk about this now in an official manner. So we are started basically in 21, the company. I will also tell a little bit later more about the company, and our spin out from the TU Berlin, and started 1.5 years roughly, and also working with Fraunhofer, and are funded at the moment with the Bundesministerium für Bildung und Forschung, so BMBF, research and education, for the next basically 1.5 years. So without further ado, let's get into the at first an outline. So what I want to talk is to first, of course, explain MOCZ, or modulation on conjugate reciprocal zeros, which is the technical shortcut for MOCZ. I'll explain later that why it's C and X. Then I will show you, of course, the communication performance on simulations, on MATLAB simulations, and then also a demonstrator version for vehicle-to-vehicle communication, which we done with the Fraunhofer, and also show you there the results we had. Then I will explain how the sensing performance works and can be done. And finally, I will conclude with a live demo here next on my table, where I switch over the camera then. And last but not least, then tell something about the company itself and make some short introduction. Okay, so this is basically the scenario we always facing if we want to do wireless communication in a single user case. So we have a base station, for example, and transmitting to some UE. And it could be also in a broadcast with multi-UEs, but let's just focus on the very simple case, single user. And if we transmit, even if we transmit with a beam, at some point this will widen up and we will see multiple reflections. And these reflections basically have their own paths, their own delays. Yeah, and basically resulting in multiple paths with different delays and different phase, of course, and will superposition and basically add up at the receiver. There could be obstruction by object, by persons. There could be scattering by trees, for example, and whatnot. So the basic assumption, what we do in this model, so as we usually do, we try to take this real world propagation and try to write it in the most mathematical simple form in a time discrete baseband. So we have here complex vectors. X is the transmitted signal. This is basically the red dash you can see there. It's like a pulse, a block basically with length of k+1. So we assume we sampled here already everything at a given bandwidth W. So the sample period is the inverse of the bandwidth in the baseband. And that we observe a multipath channel which has L taps. And these L taps can basically resolve up to L different delay paths, right? So the number of paths here shown are 4. So this is L would be 4 would be the maximum. If L is 4, it would be the maximum we can resolve. So of course, usually L is much higher than the dominant path we see. And at the end, we receive a signal Y, which has dimension n. So that's just the sum of k and L. And this is given by linear convolution. So there's no cyclic prefix. This is no circular. This is just a plain linear convolution. And in this case, let's assume for simplicity, this is noise-free. And the channel is linear time invariant. This means over these n samples we observe at the receiver, we assume the car didn't move so far and the channel is static. Now, basically, what I tried back in the days, also during my PhD, was to solve the very classical old, probably 100-year-old problem is to blindly deconvolve, which means reconstruct X and H from the observation of Y. Clearly, this is not possible because I might give you a very simple example. Take everything one-dimensional. Y is the number 1 you observe. Then X and H can be A and 1 over A. And A can be actually even many complex numbers. So you have infinite, many uncountable ambiguities. So up to this scaling ambiguity, this definitely cannot be done. So that is the bad news. But the good news is that actually, if you go to a higher dimension, then you can resolve all the other ambiguities except the scaling ambiguity. And that is what MOCZ basically did. Okay, I will explain on just one single slide how basically the blind deconvolution problem under certain constraints is basically solvable up to a global scaling. So let's start with the time discrete baseband model in the time domain. So we have Y as H convolved with X. This is a linear convolution. You can also write it as a matrix form where H becomes a banded triplets matrix. And also you can write it component-wise as the sum. Yeah. So this is something we don't usually like because we don't want to equalize anything in the time domain, especially if we have multipath and not a line of sight path. So what we usually do is we go in the Fourier domain. And the hope basically in the Fourier domain is that this very, let's say, sum product things reduce to a simple product of one basically channel value per frequency. So the idea is to parallelize the multipath channels in the frequency. That is the whole idea about OFDM, right? And that works. So if this is basically the channel is known in the frequency, we have our parallel channels, we can do water filling, a transmitter and receiver, estimate, and everything is nice. So we just have basically, if you have n subcarriers, we have n parallel AWGN channels. Okay, so for that, of course, we will need to know what is the channel on each frequency. I wrote this in this a little bit unusual form with this capital Y and X and H. And maybe some people from older generation with digital signal processing know that this is also the Z transform and or the Z or transfer function of the vectors Y, H, and X, or the finite impulse response filter in this matter of case, because it's all finite dimensional. And if we evaluate that on a unit circle, then well, we get the Fourier series. So the first idea here is, okay, if the Fourier transform is basically sampled on a unit circle, samples of the evaluated transfer function on a unit circle, why not consider this on the whole complex plane? And that brings you basically to the product of Z transforms, or the product of the whole transfer function. And that are nothing else than polynomials, because we have k plus 1 coefficients we transmit, xk, and we have L coefficients of the channel hl, and both of them create a polynomial of order k, x of z, and a polynomial of order L minus 1 given by h of z. And the only thing you basically need now to apply is the very fundamental theorem of linear algebra. And that states that every complex polynomial of order k has k complex valued zeros. And with these zeros, you can also identify up to scaling the polynomial, which means this is equal to the product of z minus alpha k, that's basically a monomial of order 1, and then we have all these linear factorizations of z minus alpha k, where alpha k is the kth zero of the polynomial x of z, and multiply them up. And the leading coefficient is basically the scaling factor here, right? So x index capital K times z to the power of k gives me the basically last term in the sum. And that same thing you can do for the channel. The channel has L minus 1 zeros, beta L, which are God-given. We don't know. We have no influence to shape that. And these zeros now are unified basically with the transmitted zeros, because it's again a product. So if you set for z and y of z alpha k, then this will vanish for each alpha k from alpha 1 to alpha capital K. And so basically we receive k plus L minus 1 zeros gamma n, and k of them are the alpha k we transmit, and L minus 1 of them are beta L. So the main idea is now, well, if this is the case, then obviously the transmit zeros are not alternated by the channel, because the channel just adds new zeros. So why not transmit, if the transmit zeros are preserved, why not map the information onto the zero position of the transmit signal? So of the transmit polynomial in this point. That is basically the main idea behind MOCZ, so the modulation / actually multiplexing in the zero domain. And so now maybe the question is, so what is a good zero set which is also stable to noise and can basically decode very stable? So this is obviously a very tricky question, and we stumbled actually by that by accident. And the best configuration sequences or signal class so far we found are given actually by Huffman sequences. That was basically published by us in 2017. This was the first publication to MOCZ. There we called it short message communication and finite impulse response system identification using Huffman sequences. So we even didn't have the name MOCZ by then, but we already saw the generalization that you can, of course, take any type of zero constellation. So let me explain why Huffman sequences are so great. And first of all, here comes the name in. So we modulate on conjugate reciprocal zero pairs. These conjugate reciprocal zero pairs are these blue circles here. Yeah. So we have one inside the unit circle, which has a radius r inverse. R is larger than 1 here in this case. And we have 1 0 of the pair which is outside the unit circle of the reciprocal radius. So radius is here R. And you can see also that the phases here of the phase distance of each zero pair is equal. So basically like with an f of t, just that the zero position are not lying on a unit circle, but on two different circles with different radius, which are conjugate reciprocal. And now the idea is basically if we, for example, want to transmit 8 bits, yeah, then we need 8 transmit zeros and choose from each pair, we order them counterclockwise, starting by the real axis, positive real axis with bit value 1, then bit value 2, 3, 4, 5, 6, 7, 8. And we choose the 0 of the pairs and the inside 0 if the bit value is 0, and the outside 0 if the bit value is 1. And with that, basically, we selecting from this bit block message the single zeros. And now we just have the zeros determined, right? So these ones here. And then we just multiply this out. And then we get our coefficients, xk from k0 to capital K. And that is the digital waveform, the IQ samples, plotted here with real and imaginary part of this specific example. So we have here 9 samples because we get one more IQ samples due to the scaling. So basically 1 dimension we always lose here, which we cannot use for the data mapping. And then this whole digital pulse is just sent through a transmit pulse, so with given bandwidth. So it's basically could be even a low pass filter, and just have then our perfect band limited transmit signal with bandwidth W. And so that is basically the transmission scheme. And now you would probably ask, okay. So we're dealing here with zeros. This is never stable with additive noise. And what's happening with the channel, it can also interfere somehow. So let's look at that step by step. So first interesting observation here is that if we look, for example, we have here k equal to 6, so 6 zeros on these two black circles with radius 1.22, the outer radius. And if we place all of them inside except one outside, and this has, okay, the first video has some direction oriented thing which depends on the other zeros. But the other zeros, basically, if we noise them, so there's a noise polynomial, right, which adds to the transmit polynomial. We have here plotted in the color, so the higher the color, the redder the color, the higher the noise power. So the lowest SNR is 5 dB and the highest SNR is 22 dB. And you can see that the perturbation basically is a little bit in a circular shape, right? So it's not that the zeros jumping from one to the other or also not jumping into the other configuration point, which is important because then it would get confusion. On the right side, you see what happens if we have a channel of length L plus 1, 3 plus 1, so 4 tabs, then it will introduce 3 new channel zeros. These are plotted here with red squares. So the black squares is the transmit zeros, and the red squares here, 1, 2, and 3 are the channels. And they are somehow randomly distributed, and also, of course, get perturbated by the noise. If there would be no noise, then with probability 1, the channels will never sit on the finite 2k positions of my transmit constellation for the transmit zeros. So in that case, basically, in the noise-free case, this is there will be no problem. Otherwise, of course, if the zeros getting close, for example, like in this case here for 1, 2, 3, 4 for the 5th zero, then this could get a confusion and I could mismatch maybe the channel 0 with the actually transmit 0 at this position. So now maybe the question, okay, then I still have to identify these zeros and have to do root finding algorithms, which are costly, especially if we increase k to 1000 or something like that. So k 6 or 8 is probably very easily to manage, you say. But what's happening if k gets up? The good news is actually the coding process is way, way simpler as you might think. And the way to understand this intuitively is you're just looking at the noised received polynomial, right? So alpha tilde k and beta L tilde are already the new channel zeros and transmit zeros perturbed by noise. Then the observation is if you take the absolute value of this y of z, you should see roughly where it gets 0, there are the zeros, obviously, and you get this polynomial surface plot. So this is for k equal to 32, and we don't have a channel here, so the zeros and also no noise. So the zeros you can see are on this, touching on these two circles in the complex plane, the red and the black one is inside and outside. And now is the thing that the receiver obviously needs to know what the transmit constellation zero set is. That is the basically constellation design. The transceiver scheme needs to be known at transmitter and receiver, otherwise any reliable communication cannot work. So he knows where all the transmit zeros should be or can be. So for K32, we have 2 times 32 positions where transmit zeros can be, so 64. And we can simply decode and demultiplex in one step by just going through this 32 or 64 zeros. Basically, in this binary case with 32 phases, yeah, which is just like with the Fourier transform. So the phase of the K0 is given by e to the power I to pi k minus 1 over k, capital K. And now we just check from each K pair what absolute value of the received polynomial is smaller than the one which is smaller, then the 0 was probably the one which was transmitted. And so we basically can decode and demultiplex directly by a simple hypothesis test in the binary case. So what we need to do is to take 64 values, in this case 2k values, take an absolute value of them and make a simple comparison. And what very important thing here is that the radius r is given by a formula given by the square root of 1 minus sinus of 2 pi over k. So if k increases, right, then this radius goes closer to 1. And the reason for that is, to go a little bit back to this perturbed noise thing, is you probably say, oh, if I increase now k, then these circles will overlap, yeah, and then these noise clouds, and I cannot distinguish anymore. That's not true, because the power basically of the noise perturbation is distributing over all the coefficients, over all the zeros. So if I increase k, if I wanted to scale up the scheme, which is utterly important, obviously, then the radius gets closer to the unit circle. So you can think, oh my God, they're getting even closer together. But the circles of the perturbation at the same noise power gets also smaller. And that is the reason why the radius has to get smaller to the unit circle to get the same performance. And actually, if you increase k and leave the SNR the same, then the performance over epno, bit performance over epno will stay the same. Which means the whole thing can scale. So this formula, this radius definition is extremely important. It might be also different optimal radius. This is still open in discussion. But this formula definitely works very well, and we simulate it up to k to 2000, and with this formula it works. This is also nice because transmitter and receiver have an easily formula just from the transmitted number of k zeros, how to determine the radius. And that basically determines the whole constellation set. So the whole constellation set is just given by capital K, right? Or defined by capital K. Okay, after we decoded the message directly, we can of course decode or reconstruct the zeros, which is basically the mapping, how we map the bits to the zeros in the first place. And the good news is also this can be even accomplished with the with the path Fourier transform, with the FFT, or discrete Fourier transform, the matrix here F star. If we scale the received samples by a diagonal matrix, which has basically the power of the radius. So this is basically just pushing basically the evaluation of the Z transform on the different radius, right? And then you can just do the Fourier series. So this is basically done here in dimension n, but you can also actually do a block circular sum structure and reduce the dimension of the Fourier transform to k. Also, one thing I want to mention here, of course, this also works for higher order MOCZ. So if we not take a binary version where m is equal to, but also m4, 8, or whatsoever. So you have multiple m position for the same phase. And then you just look for the one which has the smallest amplitude. Oh, here's an absolute value missing. I just see. So this result basically was published in our first journal publication in 2019 for MOCZ for blind short packet communication, the basic principle. And yeah, let me get back to connect this to our modulation and multiplexing scheme we're using so far. Basically, I would call the mother waveform is probably the root raised cosine, the band limited pulse, and in time domain. And obviously, we can use amplitude modulation in the time domain, or we can go basically to 4 different other domains to basically modulate and multiplex things. The first one is code domain, CDMA, where we just have some linear matrix, or some matrix anyway, which is invertible, and going back and forth and basically squeeze a bunch of time samples, IQ samples in another domain, and then decode, or I mean, spectrum and stuff. And the idea is basically to get a better spectrum robustness. The second thing, probably the most widely used method now is OFDM. We have the Fourier transform to go back and forth biactively between the time and the frequency domain. And the goal is here, as I mentioned before, that we have on n subcarriers and parallel AWGN channels in the best case. And the third thing, which is heavily discussed here in the seminar, is basically to going in a delayed Doppler domain with the SAC transform, also going back and forth biactively in the continuous domain. And the fourth version I basically present here with MOCZ is a time zero domain. And the difference with this time zero domain to all the other threes is that it's nonlinear. Yeah, so the SAC transform is bilinear. Yeah, if you combine it with the Heisenberg and the Wigner and the symplectic Fourier transform, then you still have a bilinear. But the Z transform, the polynomial, is really the non-linear function you can think of, I mean, exponentially. And to go back, you can basically multiply this out, the linear factors. And this is basically done by the Vita formula, which is an iterative process. So this going back and forth from time to the time zero domain with MOCZ is a very nonlinear process. But luckily, as I explained to you before, both ways are easily to do. So we don't need to estimate the polynomials, the zeros. We can just test the zeros. And the Vieta formula is also in complexity done with k squared, if k is the number of transmit zeros. So this maybe links basically MOCZ as a new nonlinear multiplexing modulation domain in the time zero domain, or scheme in the time zero domain. Okay, some words to the spectral density. Almost flat is maybe a little bit over exaggerated, but the most important thing here is that it is constant. So which means that the autocorrelation of all Huffman sequences, that's actually the reason why Huffman was searching for these sequences, the one which have the most impulsive autocorrelation, is given by one in the middle, of course, that's the energy, and only two non-zero side peaks, and that are the maximum side lobes, which are given by minus eta. And eta is completely determined by the radius and the number k, the order k of the zeros. And what you also can see on the right, I have two plots, just doing the simple FFT of the vector x, that this is not scaling really with the dimension k, because we have this linkage from the radius that's depending on k. So basically, it's always it's a cosine over the Fourier spectrum, and then oscillating around the 1. My minus 0.4 and plus 0.4. So the Huffman sequences are always normalized in energy. So then you get basically these plots. And the interesting part here is, since all Huffman sequences share the same autocorrelation, the spectral density is always the same for all x you transmit. So that is a nice feature you know at the receiver, for example, or can also use at the transmitter. So what is the performance now? We are basically aiming here for high mobility, where we have a lot of Doppler. So our main idea is to design shorter pulses, shorter packet symbols, as OFDM can do, because we don't need any overhead of a pilot. And by doing so, we can basically go into high mobility scenarios where OFDM is basically losing. So let's start here with 50 kilometers per hour. This is a TDLC channel from 3GPP. We have a delay spread of 100 nanoseconds nominal, and then the 50 kilometers per hour at 5.9 gigahertz carrier frequency converges to 300 hertz Doppler spread. So below here you see the channel in log power. So we have through the root raised cosine resampling, you see from this 1 or 2 taps, of course, multiple taps. And on the right, you see the bit error performance of EPNO, so energy per bit over noise power. And the blue line is the binary MOCZ scheme. And you can see the scale is basically down. So we have here, of course, high SNR, so that might be not realistic. But the point is here that we compared with 3 different versions of OFDM. So one version is the Genie one. That is the best line, which only diverged at 32 dB EPNO, and also stalls there. And the reason is that OFDM is not able to estimate the channel perfectly, because it's not linear time invariant completely anymore. And even if we do a linear estimation, so linear estimation is actually the worst. So we estimate the channel on the pilots, and then in between the pilots where the data is, we have to interpolate linearly, right? And that is basically what most of the OFDM pilot equalization schemes do, and that gives the solid red line. So we have here starting to hit an error floor between 2 to the power of -2 and 2 - 3. And if you do least square estimation, which is more costly, then we get a little bit better. Oh, sorry, the Genie one goes parallel here, of course. Okay. But if we increase now slowly the speed, so now 180 kilometers, then we see that this curve is bent further and further. Yeah, and basically hitting whenever the bit error noise floor gets lower and lower. Also, MOCZ, of course, gets affected by it because linear time invariant assumption over one block is basically it's not holding anymore. Then also the linear convolution is not a full linear convolution anymore, and then the zero union is not given anymore. The assumption is not holding. But the point is here that we can, of course, also, so we try to make here a fair comparison, which is not so easy, so that we have the same length of the BMOCZ data, the same latency, and the same power, of course, and the same number of bits. Yeah, so this is here a data rate of 6.6 megabits per second. And the thing is that the big advantage of MOCZ is that we can squeeze the length of the signal below the channel length. So this is not possible with OFDM because OFDM always needs to echo the channel impulse response length with the cycle prefix to make the whole thing cyclic and to apply the FFT. So this is something what we don't need and which can bring us in regimes where, of course, data rates may be lower, but we can handle high Doppler spread. I want to show something in a V2V scenario. So for vehicle-to-vehicle communication, we did here some adaptation of a TDLC channel with 10 megahertz, so which basically sees a reflection from another car. And also added here some diversity mode. So this is also newly patented by us. And what you can, basically the idea behind that is that you can repeat the zeros for the same bits. Basically, yeah, just repeat them in a distributed manner. For example, we have here 4 bits we want to transmit and sending in total 12 zeros. And each bit is basically, or each zero is repeated 3 times. So for example, for the first bit, K1, yeah, we have the circle one, the black circle, the blue circle, and the red circle. And you can see that they are maximum separated in phase. And then the rest for the second bit and third bit and so on. So this is basically, we call this the zero distributed diversity. And so all of these 3 basically say the same bit, and you can combine them together to make just the maximum ratio combining at a direct zero testing decoder. The result, what we get for that is, we call this here enhanced 2 mode. So this is no Doppler first, so we don't have velocity mobility. We take here as OFDM symbol 64 subcarriers, like a prefix of 32. And so this gives us in total 96 length samples. And we have here 32 pilots to estimate the possible 32 taps. So the taps here is 24 of the real channel. And we do a least square frequency domain equalization and use BPSK for the OFDM. And do also maximum ratio combining here. And for BMOCZ, we have the same number of bits we transmit and the same length. And what we need here with MOCZ, I didn't explain that, I think, we always need to add not a cyclic prefix, but the guard period or guard length. So where we don't transmit anything so that we can receive at the receiver the full convolution output, which is not interfered by the previous symbols. The thick red curve is the BPSK theoretical curve. If we know the Rayleigh phase at receiver, and the thick blue one is the BMOCZ with enhanced this enhanced diversity mode of order 2. I think it's order 4. I think. And if we're cranking up this to higher speed, now we have 100 kilometers, so this is 60 gigahertz, the V2V radar frequency, and then we have a Doppler spread of 5.5 kilohertz. then you can see that basically the OFDM performance is stalling, because as you see here from the length of the subcarriers, the longer the length is, the more pilots I want to use, the higher the data rate I want to have, then I basically lose, because the channel is not stationary over that anymore. I cannot estimate the channel correctly, and because of that cannot equalize it correctly, so I'm hitting an error floor, and this becomes worse and worse the longer the sequence is. As you can see, for VMOCZ, we have only 64 length and still have here 1.23 megawatts per second with this enhanced mode. And you can see the thick red line has 1.7 megabits, which is also using here convolution codes with rate 1/2. Also tries to do maximum ratio combining even using QPSK here. But since the length is so long, 256 compared to 64, OFDM basically hits here an error flow at 10-3, where VMOCZ goes down to 2-6 and even further. So that is basically where we see the advantage of MOCZ. Okay, now I want to show you the V2V demonstrator. So we basically demonstrated with the Heinrich Hertz Institute on hardware. So we use here Ethos Research user Ps, V2 and a Mini, so the smallest versions of them, with 2 independent Intel NUCs, which are basically the digital processing units. And since we don't want to drive around with 500 kilometers per hour on the Autobahn, we use the channel emulator, which the Fraunhofer Heinrich Hertz Institute luckily has in his storage. And with that, we can basically emulate in real time on the analog signal, electrical signal, any channel we want. So we used here a multipath channel for car-to-car communication, which goes up to 500 kilometers per hour. And the scenario is a platooning scenario, so the front car wants to just transmit this dash cam to the rear car, right? Or for a truck or some platooning like a convoy. And in the middle, you see the bit error performance over SNR. I will zoom in later. And the idea is basically that, of course, the distance will change over time between the cars and also the speed. And that we basically accomplished beginning of this year. So this is working, and you can also see it at the Heinrich Hertz Institute in the showroom. And the next step will add to this the positioning and the speed of the car, which then would show an integrated communication sensing. Okay, so how we did that? So this is basically a demonstrator, not a real-time application for a camera stream. So we basically created trains. And in this train, there is a shuttle-through sequence so that we have the time synchronization for MOCZ and OFDM equally, so that there is a fair comparison between that. And each of the train consists of 3 wagons in this case. And each wagon, basically packet, has 1 MOCZ symbol and 1 OFDM symbol. And you can see here that between the symbols, there we have 100 samples of guard length to swing out the potential channel delay. The latency of MOCZ is, of course, much slower because we don't have this pilots to spend for OFDM here 64. And then also the cycle prefix, of course, for OFDM. And there's also guard band because we need to send the OFDM signal after we're done with the FFT. We have to send it through a bandpass filter, and then this is usually a root-raised cosine filter, which has some cutoff at the edges. So we cannot use all of the subcarriers in the free domain. And MOCZ can, basically. So we later also have something like that, but I will explain later. And the bit length, the message length is the same, 127 bits, or 128, one more for OFDM. And this one is uncoded so far. Speed is 500 kilometers per hour, and we use here a TDLA channel has a very high delay spread of almost 1 microsecond, 1000 nanoseconds. And the bandwidth is 1 megahertz, 3.5 gigahertz. We used here gold scrambler and random interleaver for MOCZ and OFDM. And yeah, which is basically as used in the standard. Okay, so how does it look, the transmit and receive train on the software-defined radio on the hardware? So that's basically before we transmit to the hardware, it's between 0 and 1, of course, quantized the transmit train here. And on the right side is the receive train. And you can see, of course, that the peaks are not staying roughly where they are, and that we have noise floor here. I think it's like 1050 dB, I think, SNR. And yeah, so we have to find first the Charlotte sequence, and then we can, so this is the beginning here, oops, where the red line is, and then we can decode from there the whole packet. And that is the comparison, that's the performance, the bit error I showed you in this other plot. So we have here no carrier frequency offset compensation for OFDM and for MOCZ. So that's why we have here saturating of the OFDM at 0.01. So this could be, of course, fixed by using CFO correction for the OFDM. Usually this is also done by the Charlotte sequence, but we didn't implement it here. The interesting observation here is that BMOCZ doesn't need that type of CFO compensation, which is probably a fractional CFO and is not leading to such a big error flow. So actually we going here down to 10 minus 4 almost a bit error at 18 dB SNR. And this is at speed 500 kilometers per hour. Okay, now what's with the sensing part, right? So far we only talked about communication, so how we can do the radar thing. So let me rephrase again the properties of these Huffman sequences, which were basically invented or discovered in 1962 by this D.A. Huffman, which also did the Huffman code, but this nothing to do with Huffman codes. It's a different thing he did here. And he was looking for the most impulsive equivalent pulse strings possible. And indeed, so where the autocorrelation is the most impulsive one you can think of, in the linear correlation, not a circular correlation. Yeah, there's a bunch of other sequences which have good peaky circular autocorrelation, but if you do linear autocorrelation, you can never have a delta peak unless your transmit signal is a delta. So you will always end up with at least 2 non-zero coefficients in autocorrelation because autocorrelation is symmetric. So having only one side peak is the sparsest autocorrelation you can think of. And he basically found out that these are the Huffman sequence. And the nice thing is here, this is the plot of the real imaginary part. You can see, okay, the autocorrelation is real in this case. It's always real. The first one in the center is the energy, and the left and right is this minus eta. And this autocorrelation is the same for all of the 2 to the power of k Huffman sequence. If you set k1000, that is a bunch of Huffman sequence, which all have this crazy, awesome radar property, because these are invented for radar purposes. And as you can see, if you look in the Doppler delay domain, indeed, it's very peaky in the delay domain, and even, okay, it has some noise floor here, but it even can be used in a single pulsed signal for Doppler estimation. If you're adding them together and have multiple BMOCZ in a chain, then of course you can improve the Doppler estimation here too. So this is for the length of 511 zeros or bits. Okay, so now you're probably wondering, okay, how do these guys do the time synchronization if they don't have a preamble, which is the whole point of it. And this is basically work we did in the second journal publication, the practical aspects for MOCZ, also with my professor at UCI at that time, Hamid Jafakani, 1 year later in 2020. And what we observed is basically that as I mentioned before, in the time domain also, the signal X itself, the first and the last coefficients, taking much of the energy. Yeah, because the energy of the first and the last coefficient is 2 eta. And eta is the side lobe, which I showed you before here, so this blue peak here, and is a number between 0 and 1/2. And actually, if you take this radius, so you can also, by the way, they are always real, and xk is negative, sorry, I forget here minus. And so they are determined basically by the bits and the radius and k. And if the message is balanced, so we have the same amount of zeros and 1, then this really reduces to eta. And eta is roughly, as you can see, I plotted eta over k. If I use the radius formula, something like 120. So this is basically, so it's a very small number, so 1/10 of the energy. So the x is normalized in energy to 1. So 1/10 of the energy is always in the peaks, independent how large k is. So if you're in a moderate SNR scenario, you can basically just looking for the maximum peak. If you just looking for these peaks, so that's why we introduced here a signature, CK, which has just a 1 in the first sequence and the -1 in the last coefficient, and in between k zeros. K minus 1 zeros. That should be k minus 1 zeros. I'm sorry. Exactly. So, and then you just convolve that with the noise, of course, right? And then you can, in a moderate SNR scenario, find that n0 is the number of delays you have here to find the maximum peak and the starting point of your sequence, so that you can feed that into the decoder and decode. So it's a simple energy detector from the correlation output with this signature filter, which works for all the 2 to the power of k Huffman sequence. If you know the Huffman sequence at the receiver exactly, which you can also do, then of course this performance gets much better. Okay, that is something what we want to do for our ICAS vision for V2V. This is basically a hybrid digital beamforming, which was done by Said Decoding, postdoc from PhD student from Giuseppe Creire. And here the idea is that we basically sweeping the field of view in front of our cars and want to identify the position of the target car V here, and also want to communicate. And the idea is here also to use a finer resolution of each of the capital BQ beams with as different finer resolutions. So that's why the hybrid form, which uses less RF chain. The performance for that we did in a simulator, or Said did in a simulator, and so this is with a bandwidth of 100 megahertz. We are in a 60 gigahertz frequency range for Tato-Car, and with maximum allowed transmission power, 35 dBm, 64 antennas, 4 F-chains, and we used as the beam as shaping the DFT matrix. Field of view was 30 degrees, and speed between 0 and 30 kilometers, by a distance between 30 and 150 meters. So you have always a minimum and a maximum range you can resolve things. And let's look first on the angle of arrival accuracy. There's also used beam space root music algorithm, which achieves up to 0.1 degree resolution, as you can see here. Then we have the range accuracy is 12 centimeters roughly, by using basically so we have here the threshold at 10⁻⁴ for correct estimation, so that the signal is basically correctly received. And we have a Doppler resolution in this picture here unten below of 1 kilometers per hour in the range between 60 to 80 to 100 meters. Okay, so now basically we can actually do a little bit more. We can not only sense the biggest peak, but we can completely resolve and reconstruct the channel impulse response. And this is important because, as you probably all know, the biggest challenge in radar things, if you have multipath channels, the largest peak might not be the first peak. And if you want to do range things, you would want to identify what is the first peak, right? So you need to, if the line of sight path is obstructed by something, some person, some hand, some whatever. So then this one here, for example, could be the first peak and not this one. So that is 1 or 2 or 3 samples in difference, and that gives you already a lot of wrong estimation. So the idea here is basically very simple, and that's how we actually have a fully blindly channel and sensing, communication and sensing, blind channel and signal reconstruction, is that we take the decoded message, which we can blindly decode, right? Reconstruct the BMOCZ symbol from this message, and then just perform with this BMOCZ symbol, this is our pilot, and perform a frequency domain equalization. Yeah, by, for example, extending it just to the larger dimension n, and then cut out the channel impulse response by the guard length we expect, and voila, then we have the channel. So this is done here in simulations for TDLA channel with 10 megahertz bandwidth. This is the empirical power delay profile, and with perfect time synchronization. So we know where we have to start. So this is the performance for the bit error on the left side for 3 different MOCZ versions, for 63K, 127K, and 31Ks. The thick red line is again the theoretical BPSK curve, if we know the phases at the receiver. And on the right side, you see the channel impulse response root mean square error of each of the baseband IQ samples of the channel, of the test. Yeah. So really we take, there's no side knowledge, yeah, except that the channel is always power 1 in the transmit thing. And so basically what this tells is that the MOCZ even can resolve the global phase in this case. Because we know that the transmit sequence is always the first and the last is real, so we can even detect the change in the phase. And you can see that basically scaling is similar as with the bit error, just a little bit by 1 order worse, because we're really going here for the estimation of complex numbers, right? So this is basically tells you, okay, you can really reconstruct it for each transmission independently, and then of course do a finer synchronization in time if you even want, which we also showed in the second publication, how to go back here to find also the obstructed possible line of sight channel. Okay, I don't know actually what my time is. I have no time feeling. Oh, 12:09.
It's all right. You can keep going, please.
Thank you. I prepared a live demo, and let me see if this works. Okay. First of all, maybe I can show you this video what we had here. This is just on the Raspberry Pi with the screen where we transmit things, and that is battery powered. And just with a normal Wi-Fi antenna on 3.5 gigahertz, and receiving, and at the same time, and we compare here with OFDM and MOCZ, and basically evaluate the SNR and then determine the bit error rates. So this is the fixed messages, so it's always the same message, so that we know at the receiver how to decode, right? And let me try to do this now with the. I think I need to stop share. Let me stop share for a second, and then just take the camera. So here you can see the radios, which are basically running the whole time. We have here now a GUI, and that is. Let me see if I can zoom in. Okay, 1 second. Yeah. So, yeah. This, yeah. So yeah, basically, to go a little bit closer. So the green one is the bit error plot. So this is basically a terminal plot. So that's why it's a little pixely. And the violet one is the OFDM performance. So I can now actually also switch on here to battery mode. So let me see if I can manage that. So should work. Now I can switch off the transmitter. So this is the USB charging cable, right? So, and to just see, though, this is no, there's nothing attached anymore, yeah. And that's a transmit antenna. And you see here the red one is the current SNR, yeah, and that switches around. If I put my hand in between, then the SNR curve should go down. But if I go further with distance, then the SNR gets lower. So this is just for the battery here. Or if I'm also flip, for example, the antenna, then they are not polarized in different direction, then of course also the FNR goes down. And the reason here, as you can see again, the OFDM suffers again from the carrier frequency offset, which is not corrected, and MOCZ can go down to 10-3, I think, right? Okay, let me, so that's basically the live demonstration. Let me continue to share again. And then let's say some words to the company before I am happy to go for the questions. Okay. So our founder team is consisting of 4 people. So we started 1.5 years ago. Peter Jung is already also in the call, and the co-inventor. And Dennis Virov is our expert in wireless communication, was working 10 years at Fraunhofer Institute. And Kai Heuermann is our software engineer, also since more than 3-4 years involved in the MOCZ project, which we started beginning of 21 at university. And our team is constantly growing. So at the moment we are almost over 10 people and located in Berlin in our own office, and try to build our first hardware. As you could see, we managed to have the first prototype for a demo, not prototype, let's call it a demo, because we have not, the next step would be to really transmit a continuous data stream like a video. And we also partnering with NXP, which also have a nice new SDR platform we can play around with. And really the idea is to have a full end-to-end MOCZ transceiver, which we can basically sell as prototypes in low volume market. And with that, I want to thank you and looking forward to your questions. Thank you.
Thank you, Philip, for the great presentation. I learned a lot. I think the topic is very interesting, and yeah, thank you for that. And we do receive some questions I want to ask you. Yeah, so the first question from the audience is that because you are mentioning at the beginning that we are looking for the fundamental channel model here is a linear time invariant channel, and then at the numerical results you show some plots with Doppler. So people are a little bit questioning like how robust against against the Doppler. I know that you have already shown some results with different velocities. However, is it somehow contradict to the channel model at the beginning?
It's a good question. So yeah, maybe I didn't clear that out. Let me go back to the main V2V demonstration we did with Fraunhofer, right?
Mm-hmm.
I mean, this is 500 kilometers per hour. That's pretty high.
That's right. Yes.
And we transmitting here 127 bits, and we're achieving 10 to the minus 1, 2, 3, 4, 5. Yeah, I mean, this is already basically the proof for us that OFDM cannot cope with this high change in the channel because the OFDM, as I explained, needs with pilots and cycle prefix too much overhead, and even if it would and I also have to track all the time the channel, how it is changing, right? So it cannot say, okay, I'm done here with my pilots, I just only send pilots, and then the channel is constant, right? It has to do this all the time. And
Yes.
that's exactly where the benefit of MOCZ basically lies. In a
Yes.
completely streamed scenario, we wouldn't be probably, so if the channel is static, then of course OFDM will win. But if, especially in a scenario where the channel is changing very fast, you can, and it depends also on the sampling rate, right? You
Right.
can
Yes.
design MOCZ symbols which are 10 nanoseconds long.
Yes.
So how
Yes.
fast you have to move that the channel is significantly changing then.
Yes.
So
I think that.
this is exactly the point what we want to show further and demonstrate, but this is basically the major point here.
I see. I agree with you actually. But however, as you already mentioned, like that also depending on the sampling rate, right? For example, if we consider OFDM, but with a larger subcarrier spacing, therefore it can somehow still work in this Doppler case, even though you may lose some of the data rate. Have you ever have this kind of comparison, like how much data rate it may lose in order to have a reasonable error performance?
But that, yeah, I mean, this is what we tried here to do, right? So we try to
No.
push OFDM into the scenario, right? So this is not something, this is not a 5G OFDM physical layer. This is something we came up with. And
Right.
as you can see here, this is it's not a regime where OFDM would like to operate, because 10% or 20% of the carriers you only want to waste for pilots, right? Inside the
Right.
packets. So what we do here is that we have 120, yeah, we have 64 basically datas, and then QPSK, I think, and half of them are basically gone for pilots, and the other half is gone for guardrails. So that is not a scenario where you would probably like to drive OFDM, and still in this scenario,
That's true.
OFDM cannot handle the performance with MOCZ.
Okay.
Yeah. So this
Right.
is so the answer is we believe that that you cannot push OFDM in this corner case, let's say, yeah, because spectral efficiency goes basically to the toilet, yeah, and you are only the whole time continued with estimating the channel, yeah. It's not also in the computational cost, it's high, right?
Yes.
And I
Right.
think the same actually might also happen with OTFS, right? That is also, so you have complexity then to estimate the channel equalize. And
Right.
if the scenario is kind of static, or the mobility is kind of continuously, yeah, and you can predict things forward, it's fine. But imagine just one short package,
Right.
no return channel, no acknowledging or whatsoever.
Right.
Cars are flying by, and then they see each other for a millisecond, and then it's gone. So, or planes or satellites.
Right.
But so that scenario is actually, we are thinking MOCZ is basically an advantage.
I see. I agree with you. And you also mentioned during the answer is like when the block length is relatively short, right? So I was also wondering, like for example, in a relatively longer code word length, and perhaps like because you are doing everything in the fashion of blend estimation and equalization. And I was wondering if I actually have the possibility to afford pilots, if I can, for example, perfectly estimate the channel. Do you think MOCZ will still outperform OFDM?
Sorry, can you repeat? You mean
Yes.
can know the
Sorry. I
channel
mean,
perfectly, or?
yes. I mean, like for example, we have a very long block length, and we are working like, and we can put pilots for OFDM. And in this case, if the channel state information is perfectly known, do you think MOCZ will still win for OFDM in terms of performance?
Yeah, but the thing is, right, if you have a long block length, right, and long FFT,
Right.
then over this n samples, the channel has to be static, right?
Uh,
Linear time invariant. Otherwise, you're, if
right.
this is not is this not a convolution, you can also not do FFT and
That's
the
true.
circular trick, right? So you
That's
have
true.
to freeze down the length if the Doppler is too high. If the
Right.
Doppler is low and you are in scenarios where you can make this so long, and let's say you have this 10 or 20% of pilots you only need for the subcarriers, then OFDM will win. Sure.
Okay. Okay. Yes, I think that that's a really good point because this frequency selectivity and plus Doppler that well really requires a very stringent requirements for the OFDM to perform well. However, if for example if you compare MOCZ with OTFS in the sense of doubly selective channels, and do you think if the packet length is long, do you think which one will perform better?
Also I think so again it depends if the channel is static and you can afford longer packet length, then of course you are in a better position with OFDM.
Okay. Okay.
So
Right.
so this
Right.
is about this is yeah, so this scenario is of course, yeah, the one. So this is what I would call more the static scenario. And then, so as long as you are able to be in this regime where you only need to spend 10 or 20% of your resources for estimating a channel, and then the channel is constant, and you have a good estimation because the channel is not so long anyway,
Right.
then you're good with OFDM. But
I see.
I think that is not what we don't try here. So I also want to say, I don't believe that there's one physical waveform which rules it all.
Of course. I
Yeah.
agree with you.
So, and
Yes.
MOCZ is not a replacement for OFDM in all scenarios. We don't,
Hmm.
this is not what we see. We see
Right.
MOCZ in very short message communication on a very high mobile environments as the one solution. It could be also the crutch. Yeah. So the random
Right.
access channel where you estimate in between and establish a link, and
Right.
then tweaking on and so on. This is also possible. But
Yes.
I think that's, let me see.
Yes. Thanks for the answer. And let's move to the second question. There, yeah, there are some audience are curious about this practical performance in terms of, for example, PAPR, out of band emission, and also potentially the rate loss. And yeah, if because you mentioned, I remember in one of the slides, there's supposed to be a guard space, especially in the short length transmission that may cause some data loss, data rate loss. So do you have an evaluation on these aspects?
So first of all, PRPR is obviously visible already in this picture, as you see.
Yes.
So the first and the last coefficients is the one which I said 1/10 of the energy is usually taken. That tells you, well, okay, if K gets large, then this will create a bad PRPR. So it's similar a little bit with OFDM. And I think also the OTFS community recognized it, that if you want to do positioning, you need some good communication at the same time. At some point, you have to pay with PRPR. You cannot
Yes.
do this constant in time and frequency. Yeah. So this
Yes.
is something which has to be at some point. There is ways with this diversity modes where we also can reduce the PRPR with this repetition mode.
Right.
But what I also want to, or showed you, right, that this is also good because we know where the two peaks are, the largest peak. And we can use that information for blind synchronization.
I see.
So, and that is also an advantage, which is nice if you want to have a fully blind scheme. I mean, if you have the Shutter-Through sequence always here on left, then we don't need MOCZ, right? So, so
I see.
just to have this synchronization performance out of the game. But if you
Right.
would do that, then it's also the question if you have just one Shutter-Through sequence and that as preamble in front of that, drives down your spectral efficiency even further. So we can really do everything in one shot with that. But have to pay with PRPR.
Right. I understand that. Yes. And yeah, what about the out of band emission? That basically the effective bandwidth of the transmitted signal. Because here you, yeah.
Yeah, that's a good question. I have actually a little bit of a backslide for that. Let me go through this. So what we basically also use in the performance in the demonstrator is a guard zero band. So as you do for the Fourier transform, you have a guard band. So the
Right.
left and right carriers you don't use. And I showed you, I think, the spectral
Yes.
density of the Huffman sequence. They're all the same. So actually the peaks are at the corner. We have to circularly shift this. And so if you apply root raised cosine, which is finite, it's truncated, right? You always will have this roll of factor and then cut off some of the edges. And since now the modulation is not in the frequency but in the zero domain, you have to basically, certain zeros are affected. So the one which are here in the center, yeah. If you evaluate it on a unit circle, you get basically a frequency response. So these zeros in this area, in this guard pizza slice, we call it, basically we don't use. And we still transmit there something, that we have this Huffman sequence pattern or this uniform phase thing. And we also can introduce a DC zero at Z equal to 1, which would be sit here. Then all the Huffman sequence or all the MOCZ signals are DC offset free.
I see.
And that's also very nice, what you would like to have. So this is the way basically how we do this equivalent guard band filtering as with OFDM. For example, in the simulation I showed you, we used 13 guard zeros out of this 128.
Yes.
So we just lose only 10% to guard band.
Yes, but this guard band length is somehow proportional to the CP length for OFDM. Is that correct?
No, it's just a coincidence. That's 10% now. So, but the cyclic prefix, so the guard bands, right? They're coming on top to the cyclic prefix, right? Cyclic prefix is circular, but you still cannot use all your subcarriers you have available, and that is basically the equivalent.
Yes,
so,
I remember you mentioned there was one thing, because you have for example, 2 MOCZ transmissions, but you need to have a guard band that is supposed to be larger than the channel types, right?
The guard length and time domain.
Guard length in the time domain.
Guard length and time domain has to be as long as the Shannon post response length.
Yeah, that's actually exactly the requirements for CP, right? For OFDM cases.
Yes, with OFDM you would transmit the cyclic prefix there.
Yes.
So the nice thing with OFDM is that if you want to continuously transmit samples, right? Power, don't switch the signal off in between, then this is done. This is nicer with OFDM. So you can kind of have a continuous power you transmit. So with MOCZ you always have to basically shut down the transmission in between.
Right.
You don't have intersymbol interference.
Okay. Yes.
I'm Young. Can I add something? So
of course.
Maybe I don't know if I can switch off my camera. No,
yeah.
Okay. So concerning, let me add a comment also on the question about PRPR. So maybe many of you probably know the paper of Verdu, spectral efficiency in the wideband regime.
Right.
Yes. And there's a fundamental result saying that if you want to do non-coherent communication, we don't know the channel at the transmitter and the receiver, you have to be peaky. There's no solution around that. If you want to be non-coherent and spectral efficient, the signals you have to use are peaky. So when we somehow don't want to spend energy for pilots, so we are in the non-coherent regime, we have to live with peaky signals. There's no way around.
Yes.
So even if you have solutions for that, that goes on to the data rate. That reduces spectral efficiency. So there are also no other schemes which can do non-coherent communication and are not peaky. They have much lower spectral efficiency.
Right.
Okay.
Okay. Thanks.
Thank you.
Thank you. Okay. Yeah. Still about the rate loss, I remember that somehow it's one of my own question. Because we are actually modulating our informations on the polynomial zeros. However, if we transmit a all zero sequence, it's always corresponding to a zeros of the polynomial, right? Yeah, I mean, sorry, maybe I was wrong, and I was a bit rusty with the Z transform, but I want to say that perhaps it occurs to me that there is always a sequence that belongs to the zeros of the polynomial, which is an all zero sequence, right? Because you are actually modulating your stuff on the Z transform, and it's in a fashion of a multiplexing. Sorry, multiplication. Therefore, I would say, do you think like a all zero sequence will always be one of the zeros for the one of the solutions for the polynomial?
Let me try to switch. I think this is oh no, it's freezing.
That's all right.
It should go so quickly. So I think this is an important point, and a lot of people get a little bit confused by that. And let me be as clear as possible about it. So, so basically, right, we receive these IQ samples, which are final impulse response filter, and that is the polynomial. So there is also a zero polynomial, x of z equals 0 for all z in the complex plane. That polynomial is the polynomial 0. All the coefficients are 0. So that's the only polynomial with vanishing everywhere. If you have k complex numbers, k coefficients of the polynomial, then by the linear theorem of algebra, you have k complex numbers where the polynomial is vanishing. And that is unique, kind of. Each other polynomial, which has the same k zeros, will have the same coefficients up to the complex scaling.
Okay. Yes.
So this is done. This is just it's kind of it's bijective, if you want so, up to the scaling, and you can go back and forth with that. And that's why it is really the zero domain is really
I see.
third domain like the frequency domain. Yeah. There's only one x which have fx as the carrier frequency, as the Fourier vector, right? Because that is an invertible unitary matrix. And difference here, that's why I stated this drawing with this picture here, right? Is that we have here a nonlinear way, but still be active, way, nonlinear way from the time to the zero domain and back. That is really the thing which makes things really weird, complicated, and this is not too complicated and not stable and so on. But the fact if you're choosing the right constellation of the zeros and the right polynomials, this is actually really working and is stable and robust against the channel and the noise.
Yes.
That is
okay, thank you for this. I really like this idea because it's actually different from most of the designs of the existing waveform, and I think it really brings in some new insights. Therefore, I like it very much. And actually, in this picture, I would like to also follow up on one of my own questions that you are actually refer to this as the time zero domain, right? But I wonder that you can also do something like a frequency zero domain. Right, you put your MOCZ symbols in the frequency domain. After you have your polynomial, then you transform into time, and then transmit. Do you think that also works?
So what I mean here with time zero domain is you have this time frequency domain with the OFDM, right?
Yes.
So each time slot is one OFDM symbol, right?
Yes.
And you take this OFDM symbols and the n coefficients in time, make the Fourier transform, and then you get your n subcarrier values. And these you modulate with QAM, each of them independent, right? So, and that's why I say, okay, we don't have this Fourier transform. We go with this Z transfer or with the eta formula back and forth and have then the zeros. But the zero, the complex zero number itself is already also modulated. Yeah. So there's no QAM anymore because this pizza slices thing is changing that. And that's why I call this basically the time zero domain, equivalently this time frequency domain for OFDM.
I see, right.
And to go into to transport a MOCZ into the frequency domain after you're done is because in time and in frequency domain, all the coefficients are dependent on each other. You don't have dependency of the coefficients. You have independency in the zero domain. right? This is the idea. So that's why this is the idea of multiplexing. If you want to do multiplexing, you need independence in the domain you are. And what we do here, maybe that if this gets done. Here. So do you see here this pizza slices? Yeah, think about it as a huge pizza. You can kind of, it's infinite in the radius, but you can kind of look only at the two big radius, and you have this gray and white pizza slices here. And
Right.
each one basically is the constellation set. If you take one, for example, each of the subcarriers has the whole complex plane for their QAM modulation. Here, all the k zeros we transmit, or 2k constellation points in this case, have to share the same complex plane. And we differentiate between them with the phases. And that's why these pizza slices form.
Yes.
And that is, and then the nice thing is also if we decode them, we can decode them independently. We don't have to, so there is not much, almost no correlation between these neighboring pairs.
Right, right.
That is what you need to demultiplex independently. Otherwise, you are in a CDMA case again.
I understand. Yes.
Right?
I think yeah.
Can I add something? So
yeah, of course.
In principle, so we do this in the time domain because we have a convolution in the time domain, and we want to be somehow not estimate the convolution kernel.
Right.
So now we could imagine that we have a convolution also in the frequency domain.
Exactly. Yes.
Yeah. So if you have, for example, time selective, right? So we have a high velocity or some weird weird Doppler stuff, right? We could write this as a convolution in frequency domain.
Yes.
And obviously we can then also put the MOCZ symbol in the frequency domain. So then, so I think your question somehow is in this direction, right?
Yes, that's actually basically I want to mention. And build upon that, I would also like to see the possibility if you can do things jointly in both time and frequency. Right. So therefore, I think this is already somehow related to OTFS in some sense, even though I think what you have done is actually a more interesting transformation that you can start from this one-dimensional thing to two-dimensionals and perhaps try to estimate delay Doppler at the same time, or I'm not sure here.
Yeah, so time frequency, right? In OTFS, we always think about convolution in time and frequency simultaneously.
Right.
This is an approximation. This is not exactly correct, right? We always have to think for OTFS, we have to think about twisted convolutions and twisted things. So this means it's not a 2D convolution. It's in the first order a 2D convolution. So up to this first, so in this first order approximation, one can easily extend that. But this first order approximation could be good and bad. It really depends how you design your OTFS system, right? There are many open things.
Yes. Thank you. That's a really good answer. Thanks. Okay, I think that's the last. I have one last question from the audience. It's about the post shaping. You have demonstrated everything in a discrete fashion. There are people wondering how to do post shaping. Is that also compatible with, for example, OFDM or single carrier transmission?
I mean, that's the right slide for that. So as you see there, that's the root raised cosine, right? And that is just convolved. Or basically the IQ samples are just sampled on that one.
Right.
And then you sum this over as you do, right? So this is the Shannon-Nyquist band limited theorem of a finite sequence on a band limited pulse. I mean, you can also take a sync pulse, but it's practically not doable, we all know. So you will have, of course, some leakage out of the band, so it's never perfectly band limited.
Yes.
But that works. I mean, this is the same pulse also at the end of the day, OFDM will see, you know, after we're done with the multiplexing and FFTs. So this is, and the nice thing is you technically wouldn't need another bandpass filter for that. I mean, you have, this is still baseband. You would up convert them, of course, to the carrier frequency, and then you have your bandpass again. To make sure that because all the filters and the analog components are not perfectly, so you need to cut out some leakage then. But there's nothing really to do here. And also At the receiver, the receive pulse is the same, yeah, and then you just sample what you receive, and then you reconstruct your Y signal.
Right.
And,
Yeah.
yeah, that one.
Yeah, I think so. I think like eventually this whole thing follows like a single carrier. You have already your time domain sequence, and then you
A
just
single
use.
carrier, yes, sure,
Yes.
you're absolutely right. It's a completely single carrier system, yeah,
Yes.
because we have
Yes.
one transmit pulse,
Mm-hmm.
and the time samples are completely correlated in time and
Yes.
in frequency, but
Yes.
can be separated in the zero domain. That is
Yes.
the main thing. So it is kind of a smart CDMA fashion, you could say,
Mm-hmm.
with the difference that it's a very nonlinear transforming,
Right.
and it becomes independent there.
Mm-hmm.
So,
Yes. Yes. Do you want to add up something, Peter?
No, all good.
Ah, okay, okay, that's all good. That's all good. I think that's a very, 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 very good answer, and it's also my personal idea. Is like I agree with you guys, and yeah, I think that's all the questions I have collected from the audience. Yes.
I would use the chance here also to encourage everybody basically to approach us if there are further questions or if there are some more interest and so on. Because I mean, as for the OTFS community, right? So there's a large people now who are working on the OTFS waveform because a single company cannot do everything by itself.
That's
And
right.
our main goal at MOCZ is basically to get this into product, to get this in the scenarios which maybe are even today not doable, yeah, and really make there an impact, yeah. And we have a lot of challenges to fix also on the hardware side. So some we did with the Garzios,
Right.
but there's also going into multi-user, which is of course an important thing. And there's a lot of still of open problems, of course, for MOCZ,
Right.
which we will not be able to do ourselves, and we are welcoming the whole academic community in this case also to basically to work on that, and we are basically also free for collaboration.
That's very nice. Thank you. Yes, I think this is actually quite interesting waveform, and because recently there are some new waveforms coming up, that's why we actually want to have this from our OTFS SIG. We want to have this platform for new waveforms to be here to present, and I think MOCZ is one of a very interesting kind that is actually different from most of the existing stuff. So yes, I agree with you guys. There are a lot of things for academia that we can work on this in terms of